Okay, classroom discussion, chapter 1. First problem, age of the universe is about 14 billion years. By the way, this is a scientific fact, 13.8. If you want to be more specific, we just haven't found any galaxies older than that. Maybe we'll find something later and we'll update that number. But as of today, it is about 14 billion years. And we have to write this number in powers of 10 for years and seconds. First of all, forget years. Every time you want to do some calculations, like real calculations, you have to convert to seconds. It's only seconds. But before seconds, you want to go from 14 billion to a scientific notation for years. So billion, you have to recall the prefixes. Billion stands for 10 to the power of 9. So 14 billion, it's 14 times 10 to the power of 9. You multiply by 10 9 times. That's what's given. And you convert it to the scientific notation by putting a decimal in between. And it's 1.4. And if you move the decimal to the right, it was 14, now it's 1.4. You have to multiply by 10 one more time. So instead of 9, you get a 10, power of 10. You multiply by 10 times. So same value here and there. And then you convert to seconds, which was the point of discussion for lecture. And it's not 12 anymore. January 2nd, February 2nd, going away from jokes. It's the real conversion to seconds, 31.5 million. And converting this to scientific notation, you move the decimal, and instead of 31 million, you got 3.1, and then the change, and it's times 10 to the power of 7. So you take this number, multiply by 10 7 times, you should be getting this value. And that's just 1 year, right? How many years do we have? We have this many years to work with. So 1 year is this many seconds. That's your conversion factor. And you got this many years to work with. So you write down the number that you work with. And then you use your conversion factor written down as top and the bottom rather than the conversion factor and cross multiplication. See how years go down. You have to put years to the denominator so you can cancel years and you'll be left with seconds. So you can only say seconds here because years cancel out and seconds stay. And for that, you multiply 1.4 times 10 to the 10 times 3 times 10 to the 7. And this is a perfect example for rapid estimation. So let's say I don't have a calculator. What do? First of all, I work with powers of 10. 10 to the power of 10 times 10 to the power of 7. What's that? Well, if it's multiplication with the same basis, you add the powers. So 10 plus a 7 gives you 17. So power of 17 makes sense because it's 10 to the power of 10 times 10 to the power of 7. Be careful, it's different from 10 to the power of 10 to the power of 7. If it's power to the power, you multiply the exponents. Well, that's basic algebra. But it's 10 to the power of 10 times 10 to the power of 7. So you instead of multiplying the powers, you add them up. And then it's 1.4 times 3.1. this is like 1.5, and this is like 3. 3 times 1.5, it's 3.5. Half of 3 is 1.5, so it's 3 and 1.5, so it's like about 4.5. So your rapid estimation gives you 4.5 and 10 to the 17th power, which is not too far away from the actual truth value. Should make sense. Let me know if this is still confusing. But perfect example of rapid estimating and your conversion factor. Yeah, if you put years on top and seconds at the bottom, what's going to happen? You'll get years squared divided by seconds. That's not what we want. We want seconds. The problem was for seconds. And we got seconds because years cancel out. Okay, chat has no questions. Moving on. Okay, we measure something with a stopwatch, and there is a 0.2 second uncertainty because of a human reaction. What's the percent uncertainty of hand time measurement of 5.5 seconds, 55 seconds, and 5.5 minutes? First of all, every time you see minutes, what do? You say, oh my God, that's not System International. The very first thing you do, you convert from minutes to System International, which is seconds, and then you can do the rest. So don't you ever even try minutes, years, miles, none of that. Only seconds, meters, and kilograms. Okay, percent uncertainty is a simple formula. You got your discrepancy, which is given. You got the actual measurement, which is given. Seconds cancel out. See how seconds cancel? So you're left with no units. And you want percent. It says percent uncertainty. So you multiply by 100%. And you get about 4% uncertainty, which is okay, but can be better, right? Can be less of a number, which is exactly what happens when you measure larger amounts of time. See how for 55 seconds, the same uncertainty gives you only 0.4%, which is, 10 times better, more accurate. So your human reaction time is actually a big deal. And the more the time interval you want to measure, the less importance of human reaction is present. That should make sense. Finally, like I said, 5.5 minutes, you can't do anything with minutes. So you have to get rid of seconds. So you have to convert 5.5 minutes into seconds. And we have 60 seconds in 1 minute. So you multiply this by 60. You multiply this by 60, you get 330, and 0.2 seconds out of this large interval of time gives you an even better accuracy, which is shown. Good, clear, questions, comments? Okay, multiply taking into account sig figs. Okay, we have a question on the previous one. Would C not be 0.1 because of the sig figs? You can say 0.1. You don't have to say 0.06. You can actually round it up to 0.1. But that's what, let me do the calculations here. 0.2 divided by 330. multiplied by 100. Well, calculator shows 0.060. So that's what the calculator shows. And with one sig fig, you just have 6, and that's it. If you want to round it to 0.1%, that's fine. You can do it. Hopefully that answers your question. Boom. So let's do a tough one. You got number with a exponent, so scientific notation, times another thing with scientific notation. First of all, let's take care of units. You got meters times meters. The answer must be meters squared, right? If it's 3 times 3, that's 3 squared. 10 times 10, 10 squared. If it's meters times meters, it's got to be meters squared. So unit-wise, that's what you get. Now, let's take care of exponents. 10 to the power of 2 times 10 to the power of -1. Remember, you add up the exponents when you have the same bases. So it's 2 plus -1. 2 plus -1 is 1. So 10 to the power of 1, that's what you get from multiplying the exponents. And one last thing, you multiply 3 and the change. Let me do that. 79 times 0.068. So I do get 0.209372, which I have to round up. Because we do it multiplication, we have to go with the least amount of sig figs. How many sig figs here? 1, 2, 3, 4. 0 is in between, so it's significant. How many sig figs there? Remember, leading zeros are not significant. So this 0, not significant. This 0, not significant. It's only 6 and the 8 that are significant, so you only have 2 sig figs. So it's 4 sig figs multiplied by 2 sig figs. And you have to go with the least amount given. Least amount is 2. So it's 0 that is leading. It's not significant. And then you say 2. And then it's 0, 9. So instead of a 0, you have to add 1 unit because the next digit is 5, 6, 7, 8, 9. 10 to the power of 1 because it's 2 plus -1. And meters times meters, that's meters squared. How about that? Questions and comments? Okay, moving on. We got a hectare. Okay, back to one. You move the decimal because of the 10 to the power of 1. No, I didn't do anything. In fact, you actually have to move the decimal to say 2.1, right? Oh yeah, this is the answer. Yeah, 2.1 is the answer. If you leave it like that, it's fine. For scientific notation, though, you cannot go with 0 as the first digit. You actually have to be a non-zero. It should be 1, 2, 3, 4, 5, 6, 7, 8, 9, not the 0. But it's those details. That's okay. I'll give you a break on those. At least if you get the idea of why you rounded to 0.21 because it's 2 sig figs, and you get the 10 to the power of 1 because you're doing the powers here, and you keep track of units, that's all that really matters to me. But if you multiply by 10 one time, your 0.21 becomes 2.1. Okay, moving on. Okay, we got a hectare as meters squared. We got acre as feet squared. And the question is acres in a hectare. The good strategy here is to actually write down what's given and see what's missing. And be careful, all the conversion factors here are squared. Every time you have units squared or cubed, you say, oh my God, it's squared or cubed. It's a different story. It's a different mistake that you probably make a few times. So be careful. So units squared is always a tricky thing, and I'll explain why. So first of all, given, we got meters squared versus a hectare, and we got acre versus a feet squared. And the question is acres in a hectare, so acres are on top, and 1 hectare is at the bottom. That's what we want to figure out. So what do we have? From given, we already have acres on top. We got hectares at the bottom. So essentially, we can just multiply those two things straight across, but we have to get rid of meters squared and feet squared. So once you find the connection between meters squared and feet squared, you throw it in here. You cancel meters squared with feet squared, and you'll be left with what you need. That's the strategy. So we have to get rid of meters squared and feet squared. We have to find a conversion factor between those two things. Now, what the book has is only meters versus feet. And that's not the same thing as meters squared and feet squared. If you have 1, 2, 3, and some change, it's not the same if you get squared. Does this mean that 1 meter squared is 3 and the change feet squared? And the answer is no. The moral here is if you got linear units, just meters and feet, and you want to go to squared or cubed, then you have to square or cube the whole thing. And by whole thing, I mean it's 1 squared and meters squared. It's 3 and a change squared and feet squared. So everything goes squared, not just the units, but also the values. Okay? So it's 1 squared meters squared, 3 and the change squared, feet squared. And once you square the 3 and the change, you'll actually get something close to 11. So your conversion factor between a meter squared and the feet squared comes from squaring the linear conversion. You square the meter, becomes meter squared. You square the 1, that is still 1, but then you square the 3 and the change, and you get something that is not even close to 3. And you square the feet, and you get the feet squared. Okay, what would happen if we want volumes? Well, let's say we want a volume and we want cubes. Then what? You cube the 1, and that's still 1. You cube the meter, you'll get the meters cubed. You have to cube the 3 and the change. And cubing that will give you 3 times a 3 times a 3. That is like 27. It's actually more than that, but at least 27 because 3 cubed is 27 feet cubed. That should make sense. Be careful with units squared. Every time you have square units, you start with a linear conversion factor, and you have to square everything in that conversion factor, not just the units. So that's given. That's given. And we just figured out that 1 meter squared is 10 and a change feet squared. Now, where do you put meter squared? You have to put it down because you already have meter squared at the top. So meter squared at the top with meter squared at the bottom cancels out. And your feet squared goes on top because you do have a feet squared at the bottom already. And feet squared with feet squared cancels out. And you're left with acres over hectares. That's exactly what we were looking for from the problem. That's the math. So you multiply this by that, divide by that. 10 to the power of 4, 10 to the power of 4 cancels out if you want rapid estimation. So it's 1 times 10, divide by 4, and a change, you get 2 and a change, makes sense. And 10 to the power of 4 with 10 to the power of 4 cancels out. So 4 sig figs. Why do we have 4 sig figs? Let's take a look at what's given. We got 1, 0, 0, 0. What do we know for those zeros? They are trailing and they are to the right of a decimal. Every time zeros are to the right of a decimal point, they are significant. So we have 1, 2, 3, 4 sig figs. And those are non-zeros also, 1, 2, 3, 4 sig figs as well. So this is your rare case when you do have 4 sig figs here, 4 sig figs there. So you have to show 4 sig figs accuracy. And be careful if the next digit is 5, 6, 7, 8, 9 after 1, you have to add an extra unit. Questions, comments, funny stories? See, I made those different colors so you know what cancels with what. You have blue, blue, green, green, and the red here comes from the red over here. You really can't get lost once you work on this problem on your own after we're done with the discussion. Okay, you are in a hot air balloon above the Texas plains. You look towards the horizon. How far can you see? This is your perfect example that the sketch really shows right away. So that's Texas, and you are a certain altitude above it. And you are to find this d, this distance that you can see. And there is a radius of Earth. So that's the radius of Earth, that's the radius of Earth. And you can clearly see a right triangle, which is solved by the Pythagorean theorem. You got side squared plus side squared equals hypotenuse squared. First side is the radius, r squared. Second side is d that we're looking for. We want to solve for that distance. So d squared. And the hypotenuse is made of radius and the altitude, which is just h. So r plus h is the hypotenuse, and it also goes squared. And if you don't remember the sum of the square of the sum formula, here it is. It's the square of the first plus 2 times the first times the second plus the second squared. So this is your left side of the equation, and you keep the right side, and boom, you got r squared on both sides. So you cancel, you subtract r squared from both sides, and you solve for distance. See how I'm doing everything algebraically here? I do not plug in numbers right away. That's the general formula first, and then you plug in the values. Be careful. What you have here is meters, and then you are given kilometers. So can you do kilometers at all? No, you can't. You have to convert to System International and get rid of all the prefixes. Kilo means 1,000. So we got 6,400,000 meters. Okay. Or instead of kilo, you say 10 to the power of 3. That's what the prefix means. So either you say 6,400,000 or you say 6,400 times 10 to the power of 3 to get rid of kilo. Yeah, and the rest is given. You got 200 meters as h. So 200, 200. Radius is converted to meters. Everything is in meters, right? And once you do the radical of meters squared plus meters squared, you get meters only, squared again. So the formula is good. Distance is in meters. You can see by 51 kilometers, 51,000 meters. So just a simple Pythagorean theorem, just a little bit of algebra, and don't forget to convert from kilometers to meters. Questions, comments? Okay, we got a Jim standing beside the wide river. There's a rock, and then he walks. And see how the units are strides. You can do strides. You definitely want to convert it. And the stride is about 0.8 meters long. So that's good. We got the conversion factor from strides to meters. We definitely want to use it. And 30 degrees downstream means that the other angle is 60 degrees. And you have to estimate the width of the river. So this D is what we're looking at. So length is given, but be careful, you cannot do 65. You have to convert to meters first. And that's what we do. So first of all, how do you solve for D? It's basic trigonometry. You have two sides. You don't have the hypotenuse, so the function is tangent. Tangent is opposite over adjacent. Opposite to 60 degrees is D. Adjacent is L. So it's D over L. And if D is unknown, then you solve for D. You multiply both sides by L. And you got L tangent there, tangent 60 degrees as your answer. Oh, by the way, let me show you a trick that you probably know, but not necessarily. Check this out. Let's first of all clear the whole thing. Pay attention. Sine, cosine. You ready? Check it out. 1, 2, 3. 3, 2, 1. So far so good? 1, 2, 3, 3, 2, 1. Over 2, over 2, over 2, over 2, over 2, over 2. Red, 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 red. Yeah, if you hear the baby crying, I'm sorry. She's only 7, so she likes to cry. Many things. What does sine do? Sine is increasing from 0 to 1. And what's cosine doing? 3 to 1. It's decreasing from 1 to 0. This is how you know 0 degrees. This is how you know 30 degrees, 45 degrees, and 60 degrees, and 90 degrees. So if you ever ask me about what is a tangent, I say, I don't know. I have to do the sine and cosine first, and it's 1, 2, 3, 3, 2, 1, over 2, over 2, over 2, red, 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 red. And radical of 1 is 1, by the way, so you really don't need the radical, but I just want to show you the pattern. And it's very helpful to memorize all the common angles. So tangent is sine over cosine. 0 over 1 is 0. 1 over 0, you cannot divide by 0, so it does not exist. 1/2 divided by red 3 over 2. Division means multiplication by the reciprocal, so 2 goes up and cancels. So it's 1 over red 3. Red 2 over 2 divided by red 2 over 2. Apple over an apple. That's just 1. And red 3 over 2 divided by 1/2. 2 goes on top, so it's just radical 3. Cotangent would be the opposite, cosine over sine. This is how I remembered all the basic trig. In the unit circle, this is the sine, this is the cosine. So this is your 1, this is your 1, this is the -1, and this is the -1. So if I'm talking sine, I'm going with this scale, cosine is that scale. So cosine of 180, so we are right here, that's -1. Sine of 90, we are right there, so the value is 1. Sine of 270, -1. Okay, that was the trig part. Back to discussion. Tangent of 60, it's sine over cosine. Sine is 1, 2, 3, so it's red 3 over 2. Cosine is 3 to 1, which is 1/2, so it is radical 3. Tangent 60 degrees, radical 3. Radical 3 times 0.8 times 65 strides. See how strides go at the bottom. So strides cancel. And meters, that's what we are left with. So meters are the answers. And multiplying 65 by 0.8 times radical 3 should give you 90 for sig figs. You got 2 sig figs here, 1 sig fig there. So technically you can just go with 1 sig fig, but I suggest you never do that for this class. Please show at least 2 sig figs, okay? Even though it's 0.8, consider that 0.80, okay? For your homework, for your lab reports, do not go with 1 sig fig, go 2 sig figs. Instead of 90, you would still want to say 9.0 times 10 to the power of 1. That would be a better way of showing 2 sig figs, because 90 is confusing. 90 can be 1 sig fig or 2 sig figs. If you want 2 sig figs, you want to say 9.0 times 10 to the 1. And units are meters. Questions? Comments? little bit of trigonometry, which we will use later as well for calculating components of the vectors. Okay, this problem is what you're going to be doing in lab 1. So pay attention. You want to do the lab report. So you got a mass of 6 grams, and you got volume of this many centimeters cubed. And what do you say? You say, oh my God, those are grams, not kilograms. And we do want kilograms because that's the System International Unit. And those are centimeters cubed. Oh my God, it's not good because we want meters cubed. So your task is to convert from grams to kilograms and from centimeters cubed to meters cubed. Let's do that. So density is mass over volume. But before you do this formula and divide grams by centimeters cubed, well, you can do that, but that's not System International. Not good. I can subtract a lot of points because technically it is the correct answer. 2.118 grams per centimeters cubed is the correct answer for the problem. But the point for the lab and the course is in general that you learn System International units. So please convert to System International at all times. So here we go. Grams to kilograms, that's an easy one. Grams cancel, right? You have grams at the top, so you have to put grams at the bottom. And kilo means 1,000. So 1 kilogram is 1,000 grams. And grams cancel, so you have to divide this number by 1,000. That's the first step. The second step is centimeters cubed. And with that, you have to be careful. See how it's 1 times 10 to the power of 6. Why in the world do we have 1,000,000 for this? Let's do the whiteboard again. And let's clear it up and think about centimeters. No. Let's think about meters versus centimeters. We know that 1 meter is 100 centimeters because centi is 10 to the negative 2. So you have to multiply by 100 to get 1 meter. That's the conversion factor. And then we got cubes. Remember, for cubes, you have to cube the whole thing on the left and the whole thing on the right. And cubing the 1 is still the 1. And cubing the meter gives you what you want. You want the meter cubed, you got it. But cubing stuff on the other side means you have to cube the 100. And it's 100 times the 100 times the 100. And it means 1, 2, 3, 4, 5, 6 zeros. We have something that has 6 zeros. Or scientific notation, 10 to the power of 6. And centimeters go cubed. That's exactly what we want. So 1 meter cubed is 1,000,000 centimeters cubed. You have to cube the 100. That's how you get the 1,000,000. Okay, back to the discussion. So your centimeters cubed cancel out, and you got the meter cubed. It's kilograms per meters cubed. Those are the units for density. This is your mass per volume. Mass is in kilograms, and volume means length times the width times the height, meters times the meters times the meters. That's meters cubed. Boom. This is what you will do in the first lab. I'll give you the values in grams. I'll give you centimeters, and you will practice those conversions But now you at least have an option to see how it is done by your instructor. And of course, I will publish the correct work in Canvas once the lab is due, and you'll have a chance to see the correct answers. This is the last problem for the classroom discussion. Let me stop recording.